So how large should your off-grid battery actually be? It sounds like a pretty simple question, right? Well, actually, if you get this wrong, you're not just looking at a few flickering lights. You are looking at a completely ruined, wildly expensive system. Welcome to This Explainer. Today we're tackling what is easily the most critical and honestly the most misunderstood question in off-grid solar engineering. Let's solve this massive puzzle together.
Think of this as your masterclass in battery sizing. We're going to cross that really dangerous gap between theoretical needs on paper and real-world off-grid engineering.
Okay, here is our step-by-step blueprint for today. We'll start with a foundational mistake almost everyone makes. Cover the physics of power versus energy, dodge the amp-hour trap, and calculate our real daily energy. Then, we'll run a reality diagnostic before laying out the final system blueprint.
Let's jump right into part 1, the foundational mistake, which is sizing by your inverter's maximum output.
You know, a lot of beginners look at their shiny new 6 kilowatt inverter and think, well, I just multiply 6 kilowatts by 24 hours and boom, I need a 144 kilowatt hour battery. Look, that is an incredibly dangerous assumption. It basically assumes your inverter runs at maximum capacity 24/7, which leads to designing this unnecessarily enormous and absurdly expensive battery bank. In reality, loads cycle on and off. You flip a light switch for a few minutes, your fridge cycles, the washing machine runs for an hour. Your battery size has to be calculated by one metric, and one metric only: real daily energy consumption.
Moving on to part 2, physics, specifically power versus energy.
Before we do any math, we have to get this right. The inverter determines how much power the system can deliver at any given moment. The battery determines how long the system can supply that power. I absolutely love that quote. Read it again if you have to, because this needs to completely shift your mindset. We have to stop fixating on instantaneous watts and start thinking about stored energy over time.
A great way to visualize this is like a giant plumbing system. Think of power, your kilowatts, as the width of a water pipe. It dictates how many appliances you can run all at once, basically how strong the flow is. Energy, on the other hand, which we measure in kilowatt-hours, is the total volume of your storage tank. It determines how long you can keep that flow going. So a 1 kilowatt load running for 1 hour equals exactly 1 kilowatt-hour of consumed energy from your tank. Simple enough, right?
All right, part 3, the amp-hour trap.
Listen, I literally cannot stress this enough. Amp hours mean absolutely nothing without voltage. It's a massive, massive trap that catches so many DIY enthusiasts. Relying on amp hours alone will ruin your design. You must always, always calculate in watt-hours and kilowatt-hours to know your true energy tank size.
Let's look at why that's true with a side-by-side comparison. On paper, both of these batteries proudly slap 200 amp-hours on the label. Sounds identical, right? Well, look at the voltage. The 12-volt battery yields just 2.4 kilowatt-hours. That's barely enough to run a load of laundry. But the 48-volt setup, that yields 9.6 kilowatt-hours of usable energy. That is enough to power an entire house. Don't let marketing fool you. Amp hours alone are basically a trick.
Which brings us to part 4, calculating real daily energy.
Now we shift from theory into practice. Professional engineers use a strict 4-step mathematical formula to calculate actual battery needs, and we're going to walk through it right now. We start with the daily energy balance, move to autonomy, factor in depth of discharge, and finally account for system losses. Okay, step 1. Let's see how this builds. We figure out our true daily energy balance by listing our individual appliance loads. We literally multiply the wattage of our lights, our fridge, our pumps by the hours they actually run each day. When we add all that up here, we get our baseline, 8.5 kilowatt-hours per day. This is it. This is our magic number, the absolute foundation we build the rest of the system around. Step 2 is designing for autonomy. We have to ask, how long does the system need to run completely on its own? What if it's pouring rain and we get zero help from the sun? For our system, we're assuming 1 full day of zero solar generation. So our target useful energy stays firmly locked at that 8.5 kilowatt-hour mark. Now for step 3, the hardware protection buffer. You see, you can't just drain lithium batteries down to absolute zero without damaging them. They are typically limited to an 80% depth of discharge, or DOD. So to protect our investment, we divide our 8.5 kilowatt-hour need by 0.8. This creates a vital 20% hardware protection buffer, bumping our required capacity up to 10.625 kilowatt-hours. And finally, step 4. Actually, scratch the ideal math, we have to add a layer of harsh realism here.
No system in the world is 100% efficient. Between inverter heat and cable resistance, we have to factor in about a 10% system loss. So we divide again, and that pushes our required gross capacity all the way up to 11.8 kilowatt-hours. That is the gross number our hardware actually needs to be rated for to safely deliver the 8.5 we want to consume. Let's put this to the test in Part 5, the reality diagnostic. We're going to set up a bit of a conceptual face-off to stress test our math. On one side, we have your standard 200 amp-hour battery. On the other side, a beefier 280 amp-hour professional standard unit. Let's push both through our real-world diagnostic and see which one actually survives our strict 8.5 kilowatt-hour daily need. So watch what happens right here in Diagnostic 1. A 48-volt, 200 amp-hour battery gives us a gross capacity of 10.24 kilowatt-hours. Sounds like it might be enough, right? But wait, after we subtract that 20% depth of discharge to protect the battery, and then strip away the 10% for system losses, we are left with only 7.37 kilowatt-hours of real, usable energy. It falls disastrously short of our 8.5 target. The system will technically turn on, sure, but with literally zero reserve margin. One cloudy afternoon, and you're forcing deep, damaging discharges.
Now, let's check out Diagnostic 2. Here, we test the 280 amp-hour battery. The gross capacity is a healthy 14.3 kilowatt-hours. When we apply those exact same real-world penalties, the 80% limit and the system losses, we comfortably yield 10.3 kilowatt-hours of real usable energy. Boom! This easily handles our 8.5 baseline, it provides a safe buffer, guarantees the hardware will last, and most importantly, ensures the lights actually stay on.
That takes us to our final section, the final system blueprint. Before I show you the final architectural design, let's just quickly lock in those core takeaways. These will save you from making catastrophic and expensive mistakes. Always calculating kilowatt-hours. Never size your battery by multiplying your inverter's maximum output. Factor in your depth of discharge, and please do not forget to account for those inevitable system losses.
And here it is. This is the ultimate reward for doing the math properly. For an 8.5 kilowatt-hour daily consumption with 1 day of autonomy using lithium iron phosphate batteries, you need a 48-volt system with a required hardware capacity of 280 amp-hours. This gives you a gross energy of 14.3 kilowatt-hours. You guys, this right here is a beautifully engineered system. It isn't built for the ideal conditions of a textbook. It's built to survive the real world.
Which brings me to my final thought for you. When you look at your own solar project or any system you're dreaming up, you really have to ask yourself, are your off-grid calculations built purely on theory, or are they truly engineered for reality? Do yourself a favor, go back to your own math, run it through this 4-step diagnostic, and make sure your system is actually built to last. Thanks for hanging out with me on this explainer, and keep learning.